Hello, welcome to another video lecture on projectile motion. In this video, we will look at an example where something is launched into the air at some angle. This example will follow along in your textbook in section 3.3, examples 5 through 7, the kicking of a football. Here we have some football launched into the air at an angle. The angle happens to be 40 degrees. It is launched at an angle, at a speed or a velocity of 22 meters per second at 40 degrees. There are several things that we're going to look for throughout this problem. One of them is going to be the maximum height. The maximum height is the highest point that this projectile reaches. Also known as the maximum y direction. In addition, there are a few things that we know at this point. At the top here, for the maximum height, the velocity in the y direction is going to be 0 meters per second. This is because this is the point that it changes direction and starts falling back down to the ground. The other things that we're going to be looking at are going to be the time. Hang time is the total time up and back down. And the last thing we're going to be looking to find is the range. Range is the distance the projectile travels, and that is a really bad squiggly line right there. The distance the projectile travels in the horizontal direction. There are a few other things that we know before we even start looking at what this problem is asking. For any launch in a projectile motion, the angle and velocity that it's launched at is going to be the same when it returns to that same height. So for here, when it comes back to ground level at this same height, it will be moving at a velocity of 22 meters per second at 40 degrees. So this angle here will again be 40 degrees. Now that we have this, the first thing we want to do is split up this into x and y components. So we have some initial velocity at the x direction. We want to split our values into x and y components. We're going to do this using trig. What I'm going to do is I'm going to set up a table for all my known values right now. First in the x direction. And then in the y direction. As we've done in the past, I'm going to let this point be our origin, 0, 0. So the initial position we'll say is at 0 meters. The acceleration in the y direction, since this is the vertical direction, is going to be the acceleration due to gravity. This will be negative 9.8 meters per second squared. Some other things to look at this table. Since we have no acceleration in the x direction, since it is a projectile and we're ignoring the effects of air resistance, we have no acceleration in the x direction. We can just merely erase that. Since there's no acceleration, there's going to be no change in velocity in the x direction. So in the x direction, the velocity will remain constant throughout the entire flight. In order to find the velocity in the x direction, the cosine of angle 40 times the magnitude of the speed of the velocity, 22 meters per second, will give us that component. Or roughly, using a rounding to significant figures, 14 meters per second. Excuse me. Will give us our velocity of 17 meters per second. And likewise, we will find our velocity in the y direction initially to be 14 meters per second. Now that we have this, we can start to solve for the time. The first thing that we want to do is, I always like to solve for time. It just makes it, it's usually the limiting factor. In the case of the examples in the book, they go and ask you to solve for the height first. Now, there is a way that we can do that. If we look over here at our basic equations that we use, we have this bottom one here. Final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in position. This does not involve time. So we can use this to calculate the maximum height that this projectile will travel. We know from looking at our diagram that at the top, at the highest point, the velocity in the y direction is going to be 0. So we have an initial velocity and a final velocity. Doing this out, we come up with 0 meters per second squared is equal to 14 meters per second squared plus 2 times a negative 9.8 meters per second squared times our change in y. Getting a little bit crunched over there. Rearranging this, 14 squared over 2 times negative 9.8 meters per second squared equals our change in y. Our change in height, or our final position, will work out to be 10 meters. Now, using this height, we can either use one of 2 equations to solve for the total time it takes to get to the highest point. You can either use this distance equation here, or we can just simply use our speed equation. If we were to do that, we have our final velocity of 0 meters per second is equal to our initial velocity, 14 meters per second, plus our acceleration, negative 9.8 meters per second squared, multiplied by time. Doing this out will yield a time for it to reach the highest point of roughly 1.4 seconds. This time is half of the hang time. This is the time to the highest point. So make sure to pay attention to that. The total time for flight or the hang time is going to be 2.8 seconds. Or in the book, they rounded a little bit, so I believe it comes out to 2.9 seconds. Now that we have the time, we can come back and we can solve for the final thing, the range. Very simply, we have our initial position. We're trying to solve for our final position. We have our initial velocity. There's going to be no change in that x velocity. There's no acceleration. We can use our distance equation here. So our change in position is equal to our initial velocity, which is 17 meters per second, times our multiplied by the time, 2.9 seconds. This here will give us an answer of 49 total meters. So right now we've already solved for everything that we really can for this problem. we have our maximum height of 10 meters, we know our speed at the top, we know how long the entire flight takes, and we know how far it travels in the horizontal direction. Please make sure to separate out your variables in the beginning. This should be your first step always. Now, I always like to, and I recommend solving for time next if you can, but sometimes the question you don't need to do that. But if you separate out your variables of what you have and what you don't have, it makes the problem that much easier, and it really just shows me and whoever else that you actually understand the question. Thank you very much. Have a great night. I hope this video was helpful in understanding projectile launches where objects are launched at an angle into the air. Please make sure to follow all the necessary steps when solving problems. Here I have my wonderful lab assistant, Miss Weatherhead, and I will now kick a football into the air and through the uprights. Are you ready?
I'm ready.
Here I come. Oh!